The same happens in China, I guess, and a few other countries. So in 2050, it will not be so relevant. So that's why there are so many people interested in wind energy, as I noticed from Monday up to now. So who are the big players worldwide? In first place, as in almost everything else, there's China. They have 35% of the installed capacity in the world. Second place, I'm sorry this is in Portuguese, but China, you can understand this, United States, 17%, then Germany. Brazil is in the 8th place. Okay, up to now only 2% of our electricity comes from wind power. So in the whole world there are 539 gigawatts of wind power electric generation. So just in order to show the evolution of the wind turbines since 1985 up to now, this slide shows the diameter of the wind turbines, namely horizontal axis wind turbines. These are the more common wind turbines, and these are used in wind farms. Okay. So nowadays we have turbines with nominal power capacity of about 8 to 10 megawatt, and who knows what will happen in the future. But there are some difficulties in the future, so I'll just show one slide by the end of my presentation, and then Professor Gao will go into the details about this. So this is already operating 7.5 megawatt wind turbine Enercon for onshore wind farms. Here I have a picture of the, as far as I know, the biggest wind turbine already in operation, but it's been tested up to now. I guess Dr. Zhen knows if it is commercially available or not. I don't know if it is available. It's entering the market. So this is a Vestas wind turbine. Okay, I took this from this blog, so you can find it. Just a few figures about it. Each blade weighs 38 tons. The swept area about 21,000 square meters. It compares it with the London Eye wheel. And okay, there is another type of wind turbine. We say, okay, it has a vertical axis. What's going on here? Okay. So this kind of turbine, they have two main different principles. In this one, it rotates because the blades, they generate lift. They have airfoil sections, okay? And they can accept wind from any direction, so they are omnidirectional. And this is we call it Dahiel. I don't know how to say this correctly, but I say it as I read, Dahiel vertical axis wind turbine. And this one is more simple one. It's called Savonius. It's a drag. We call it drag because the forces that rotate the turbine, they drag the blades in the same direction. Okay. And here the lift, causes a moment, but this force doesn't have the same direction of the wind, of the incoming wind. So this is drag turbine and this is lift turbine. These turbines, up to now, they are always smaller than the horizontal axis wind turbines I mentioned before. So, as I said, I have to make a miscellaneous presentation about some basic topics. So, let's talk about a little bit about wind properties. So, if you go far above the ground, you find a strong wind, it's almost a steady wind. We call it geostrophic wind. As you come close to the ground, the surface, it affects the speed of the wind. If you come very close to the ground, you know that the fluid, it has the same velocity as the surface, okay? So, assuming this is a very, very smooth surface, the fluid that is in contact with the surface will have no relative velocity, to be zero relative velocity. But this is not a smooth surface. It has some roughness, okay? So we adopt a model where we say up to a certain height, Z0, the surface of the fluid is the same as the velocity of the fluid is the same as the velocity of the surface, okay, due to roughness effect. And due to shear, the velocity of the air, the fluid, it starts from 0 and it grows until it attains the value of the geostrophic wind, which is far above from the surface. Okay? So, in order to have an expression to show this profile, we make some hypotheses and we adopt the simple law, this power law. This power law, it relates the velocity at a certain height to the value of the velocity at another height. We know this value, and we multiply by this height at which I want to calculate the velocity divided by the height of the known velocity, power to n. N, and this is a shear. Some people call it shear factor, shear coefficient, shear exponent. Just shear, it's enough to identify it. And this Z0 height, we can extrapolate it. If you measure velocity values along this profile, we can extrapolate a height up to which the velocity of the fluid is 0 relative to the velocity of the surface, okay? So here I'm just a slide in order to show how shear affects the growth of the wind speed against the height. We have the velocity at 50 meters above the ground, a value of 8 meters per second. Then according to the shear, you have this different velocity profiles. So, up to 50 meters, the less shear, the faster the velocity grows. Above 50 meters, less shear, the growth is more slow. Okay? Just in order to show it to you, how it works. This is according to this simplified power law. Okay, according to those hypotheses, we can make this, we can obtain this expression, the logarithmic profile for velocities. So here I relate the velocity at a certain height I calculated starting from a known velocity at the reference height, z(r). This is that height above which velocity begins to grow. So we call it roughness length. It is related to the roughness of the ground. And you see, if you measure the velocities at two different heights, you can calculate the shear or shear coefficient. Okay? So this is a simple procedure for you to describe the velocity profile, starting close to the ground and going to the geostrophic wind. So it's clear for us that if the roughness is not so evident, the flow will not be very disturbed. But if you have this kind of roughness, it will make a big mess in the wind profile, wind velocity profile. Okay, and you can study. I'm not going to talk about this. Different regions. You have one boundary layer here. You have another one, a messy one here, and here you have another kind of boundary layer. Okay, the thing is, roughness changes the pattern of the wind profile. So this is an important influence. Just in order to put another example, we have a wind turbine here. Yeah, and we have this different wind speed profiles, each one related to a roughness length measured in meters. So you see, in calm seas and sand beaches, you have a very, very small roughness length, less than about one millimeter or even less. Okay, if you have grass, you have about 1 centimeter roughness length. In a forest, you have 1 meter. So this is, as I said, an extrapolation. Okay, it seems low. It's very small value, 1 meter. Okay, extrapolation. Just in order to explain that wind speed profile I showed before. We can see one thing interesting here. Imagine this is a two-blade wind turbine. So you can see the blade that is pointing upwards, it faces wind with a bigger velocity than the blade that is pointing downwards. Okay? So we have different loads here. The aerodynamic load here is bigger than the aerodynamic load here. I think my light is going away. Okay, I'll make it flashing. Okay? Batteries. Oh, no, it's okay. It's not my fault. Okay. So this is a source of a vibration because it makes the rotor shaft bend. Just an easy way to understand what happens to wind turbines. Okay? Well, we saw that wind speed varies with height as a function of the ground, of the kind of surface you have. Wind speed varies in time as well. So I think this graph shows some important information. This axis is related to the energy. It's a power spectrum. Okay? And this one shows the period. Imagine it is a wave, sine and cosine, something like this, an harmonic function. Here is the period. So you have periods ranging from days to seconds. What do you see here? Imagine the velocity at a certain point of the atmosphere. It goes through a complete cycle in 4 days. So it's almost a steady value of velocity. It varies very, very slowly. Okay? So it is influenced by large-scale weather systems. So you can imagine this happens far above the ground, the surface, and it's ruled by large-scale weather phenomena. Okay. Now we have another peak of kinetic energy or of power with a period of about between 10 and 24 hours. This may be related to more local causes. For example, consider you're measuring the wind speed close to the seashore. So there is wind flowing from the sea to the land and from the land to the sea. Why does it happen? Because land warms up faster than the sea. So during the day, the air close to the ground, it hits, goes up, and the wind flows from the sea to the land. Better? Oh, okay. Thank you, much better. So, during daytime, the wind flows from the sea to the land. So, after evening, the land cools quickly and the water remains hot. So, the air flows up from the sea and the wind flows from the land to the sea during night. So there is a period. So the velocity changes during period time. And then we have another peak of energy. This is much shorter periods of time, about 1 minute and all this. Well, you see that the time scale for wind phenomena is different for other mechanical phenomena time scales. Okay? I'm not going into details. It's just a way to measure the energy of the wind. Okay? I didn't put the units here. Just a way to measure the energy of the wind flow. Okay. The more energy you have more speed and more flow. Okay. And here I'm talking about for periods smaller than 10 minutes. We call this a kind of turbulence. So the frequencies here are very, very low frequencies compared to other mechanic equipments and phenomena. Okay? Oh, there you go. I'm not lucky with this guy. Okay. Okay. This is just an example. It shows how the wind speed varies with time during a period of 5 minutes. Okay. So suppose you record the speed every 2 seconds, something like this, and you have this graph. You calculate the average velocity, and this is a measure of turbulence. How do you calculate turbulence? I think it only works when you hold it. Okay. Esse aqui e esse aqui. Okay, vamos ver. Apontar para lá. Okay. Okay. Sometimes it works. Okay. So here we have different values of average wind speed. And for each value, we have a standard deviation. If we divide the standard deviation by the average velocity, we have a measure of turbulence. Okay? So this is for a particular case, but a good example which shows that for low wind speeds, you have a higher level of turbulence. In this range, the turbulence is smaller, and then you have a scatter here result. So we can, it's quite intuitive that the higher you go, the less the turbulence, okay? So here we compare the turbulence. If you measure the velocity at a height of 8 meters and compare it with the velocity measured at 28 meters high. So you see, roughness is higher here, 8 meters above the ground, and smaller here at 48 meters from the ground. Okay? So you try to put the turbines high, away from the ground, so you have less turbulence. Okay. No. So wind speed changes with topography. So if you have a gentle slope like this, you have an increase in the wind speed profile. So this is a good place for you to put wind turbines. This is a kind of ridge of a mountain. But if the topography is not so smooth, then you may have problems, depending on the place you put your wind turbine, because you have some turbulence around the surface. Okay? So let's look what happens when the wind meets the turbine. If you take a picture of the wind profile, it won't look, it won't be a good guy. This would be the good guy. This would be the wind speed profile that one we calculated using some simple expressions, like exponential power law. And you take a photo of the wind profile and you'll find something like this. Okay, this is a little bit exaggerated. But you see, the wind speed changes from point to point. Okay? And this profile changes with time as well, that I have just showed you. So, if you describe the wind speed looking at the wind from the inertial reference, okay, let's suppose the ground is the surface is an inertial reference. You measure these values of wind speed, okay? But the blades, they face the wind with another component of speed because it turns around this axis. So you have to add speed. So you have a relative speed. So the velocity faced by the blades has this kind of profile, which much more peaks and valleys. Okay? If you consider this profile of wind speed to be frozen and you allow the water, the blades to rotate, this edge, you cut this profile and you to face a variation in wind speed values. Okay, it's easy to understand that. So all these speed variations, they make the turbine vibrate. That's good for me. So, I know we have seen this before. I guess Professor Paulo mentioned this kind of thing, so to be a very, very brief comment. What is the wind turbine's job? So consider you have a cylinder of fluid, of air flowing here. We always have very low pressures, so you can think of this as a uncompressible flow, okay? Although we have air, I guess. So this cylinder of air, this imaginary cylinder, it has a kinetic energy calculated by this expression. This is the mass and the velocity to the square, okay? So the wind turbine, it transfers mechanical energy from the wind, the kinetic energy from the wind to the rotor. The rotor begins to rotate. You have kinetic energy in the rotor. And this transfer happens at a certain rate. So we call it power. So power is calculated by this expression. What's important to note here, it depends on the density of the fluid, about 1.2 kilos for cubic meter, the area, the swept area, and the velocity to the third power. So you must have big turbines and high velocities in order to have power. So it's important to understand that if you don't have flow, if you don't have mass flowing through the disk, imagine a disk here, you don't have power, okay? Or you may have good wind, you may have a big area, but you don't take too much power. You don't produce too much power. So you have low efficiency. You also were presented to Bette's law. This law shows us that the maximum amount of power you can produce is about 59% of the available power in the wind. Okay, so you cannot build a machine in this open air conditions, which takes more than 59% of the power available in the wind. Okay. Then suppose you have a particular turbine, and you know how much power you can take with it at a certain value of velocity. You divide this power by the available power in the wind, you have this power coefficient. Okay, I'm just making some definitions here. First time. So this is a power curve of a turbine. Let's compare some things here. This graph shows you the power calculated according to Bette's limit. So at each value of wind speed, you calculate this expression. You have 0.59, this is the air density, the area of the disk, velocity to the third power divided by 2, you have a 2.4 megawatt wind turbine. Okay, this is the ideal case. This speed, we call it cut-in speed. At this speed, your turbine begins to work. It produces power. You can take energy from it. And this is the real power curve of the turbine. For many reasons, mainly safety reasons, you put a limit to the power. Okay, it's related to the generator you put in your turbine. So you start producing power here. As the wind speed grows, the power grows, and up to a certain value of power. Okay? This is nominal power of your turbine. So you see, the power you produce is smaller, significantly smaller than the ideal power you could produce. Okay?
My name is Raquel, and I wanted to know this cut in speeds. Does it change like significantly according to the size of the turbine?
Yes, if you have a, just think about the size of the generator you have to push to rotate, and you think about the inertia of the rotor. For commercial turbines, it's about 3 to 4 meters per second.
3 to 4 meters per second.
Yes, for commercial turbines.
Okay, so
If you have some small turbines, sometimes you get something close to 2.5 meters per second, but it's very difficult.
okay, thanks.
Obrigado, too. So here I show you two graphs. Again, the power curve of a turbine, now a 3 megawatt wind turbine. And here I show the power coefficient curve against wind speed. So here is something about between 2 and 3. This is a very, very good wind turbine, I would say. Is cut-in speed. So here you divide the power. You put divided by the ideal amount of power you could take, emitted by Beth's law. And as power increases, you have the power coefficient increasing as well. Then you limit the power produce. Then, since the wind speed is growing, your power coefficient decreases. Okay? So in case you have a turbine which operates in very, very high, very windy places, if you have high speeds, it's good for you to have nominal powers, nominal value of power bigger. Otherwise, you lose efficiency. You lose power coefficient. So, another important concept. Sorry for this, I took it from another presentation. There is this is an intuitive concept. There is an ideal rotation speed for your rotor. Suppose you have the wind flowing towards the turbine. Just consider a two-blade turbine, okay? So if the rotor rotates very slowly, you waste a lot of energy because the wind passes through this imaginary disk and does nothing. There is no energy transfer. The blades are here and the wind is passing here. So it passes unnoticed, okay? Now imagine, well, the rotor is rotating fast. So this would be something like, as I shown before, if you cut the flow, then you produce no power. This could happen here if it rotates very, very fast. So you're far above the ideal wind speed, rotation speed. So when you rotate at the ideal rotation speed, you have a high coefficient power, okay? Horizontal. Tá bom. Tô quase acabando. Okay. This is just another important concept for you. Because now, okay, one back. bearing that in mind, we define this parameter, a tip-speed ratio. You divide the speed at the tip of the blade. Okay, you multiply the rotor angular speed by the rotor radius, and you divide this speed value by the speed of the undisturbed wind velocity. Okay, so you have this wind speed ratio, and it's a good idea to make plots of the power coefficient against this wind speed ratio. So you have an idea of the ideal rotation speed of the rotor. Oh, I put this quote here because I took this figure from this book. And this professor, in fact, he was invited to give a lecture here, but he couldn't. He's a very, very old man, and so he preferred to stay at home. But in his book, he says that Savonius rotor has a higher power coefficient than the traditional American multi-blade rotor. Use it in, you find this American multi-blade wind turbines when you see Western movies. You see lots of these American multi-blade turbines. They use them for pumping. Okay. Most books show this. They say this is the Savonius graph and this is the American multi-rotor. So I guess American multi-rotor say this is, American books says this is a graph for the American multi-blade, and the other books say this, maybe German, I don't know, this is the graph for the American multi-blade. Okay? So, but what can you see here? That they attain their maximum power coefficient at low values of tip speed ratio. Okay? So here you compare the two-blade turbine, a Dahil rotor, that one with vertical axis, and there's a graph showing the Dutch four-arms windmills. You find many of these windmills in Holland today. So, wind turbines vibrate. That's nice for me. Oh, just consider wind turbines. They are tall, they are slender, so they are very elegant, and they look like top models. And they point their nose upwards, just like top models. And they shake, they vibrate, just like top models. So they look very elegant. But they're not proud. They're just pragmatic. Because since they vibrate, you consider the tower vibrates, the blades vibrate. So you don't want the blades to hit the tower. So you have to find ways to avoid this happening. So you point the nose of the nacelle, this thing is nacelle, upwards. So have a tilt angle here. And you can shape your blades like an umbrella. They call it three-band. And you can also put the root not in this red plane, but you make a kind of pre-coning angle here. So you have a greater distance here, tip clearance from the tip of the blade to the tower. All this because it shakes. It's elegant, but it shakes. And you don't want to destroy your turbine due to vibration. Okay? This one, the next. So, just a simple example of how we study vibrations of wind turbines. I did this with 7 degrees of freedom degrees of freedom model. A very, very simple model. So let me show you the tower band. So I put a degree of freedom here, the angle theta. There is a degree of freedom for each blade. Theta B1, 2, and 3. You have torsion here, and so 2 degrees of freedom here. And I studied the effect of what we call kind of unit mass vibration absorber. A kind of big pendulum here. Just put a pendulum here. Not too crazy. This happens in real systems. I'll show you some photographs. And I also put some stiffness value and some damping value in this system. There's a 7 degree of freedom. I wanted to study the effect of this pendular unit mass vibration absorber on the vibration levels here on the top of the tower. So this kind of vibration absorber only works at a narrow range of frequencies. Okay. So I'll show you the results here. Oh, one back, please. This one. So here we see the time, and here the displacement at the top of the tower. I'm sorry it's in Portuguese, but measured in meters. It's a small turbine, so the displacements are small as well. So as the wind acts on the turbine, there is a thrust force. Okay? So due to this thrust force, there is a static deflection of the nacelle as a whole. Okay? It's pulled backwards. So this is a static value. And due to some excitations, I considered aerodynamic loads. I considered, in fact, aerodynamic loads and gravity loads and other kinds of loads. But one of these loads, it caused resonance with the first natural frequency of my turbine. And I want so I tuned the mass absorbers in that frequency to see how it works. Okay, let me go back to one slide. Physically, this absorber, it applies a force on the same frequency of the vibration of the system. So the force tries to put the system back to its original static equilibrium position. That's how it physically works. Okay? It must have a certain magnitude and the same frequency of the vibration of the device. That's how it works. And I compare here the vibration amplitude without the mass absorber and the vibration amplitude when I put on the vibration absorber. So it reduces the vibration amplitude to the half. So a good effect. But there is no free meal here. Here we have to consider that this must be a heavy thing. So you have to consider a mass here. You consider the mass of the nacelle and the blades and a part of the tower, and you divide it by 20, and you have to hang it here. So it's not a very good idea indeed. But some guys try it. I'll show you some photographs. Here you can see this big donut, biscuit, I don't know. It's a kind of pendulum. So here they put it in a vertical axis wind turbine. I show this because Professor Zhao studies this kind of things. Maybe he can talk about this more for us. So you put this donut here. You just don't only hang it, but you try to make it more effective. Okay. Just other examples here. This guy, he put the platform inside the tower. No, there is a gap between the platform and the tower, and maybe he puts a spring and a damper here. But most times they put the donut outside the tower. Okay, so they hang it with these cables and put springs and dampen devices around it. So as the tower shakes, this thing acts as a tuned vibration absorber. And now I mentioned in the beginning that there is a kind of barrier in the size of wind turbines. So just press it for me, please. What? No. No. Advance, please. Stop it. Two slides back. This one. Yeah, okay, I try to do it. When I get close this way. No. Okay, it doesn't work. Okay. Here we have what could be a design for a 10 megawatt wind turbine. Why do I show you it? This is a solution for a 10 megawatt wind turbine. The guy put it on 3 legs and then a single tower, and he puts several generators up there. But what I want to point out here is this. In this design, note that there are many elements related to vibration mitigation. Okay? And this is a part of the solution. If you want to make big wind turbines above 10 megawatt power, you have to cope with severe vibration issues. Okay, so the solution passes through vibration mitigation devices. Now, I have to mention the main components of a wind turbine for those who are not used to it, just in order to see the parts of it. So here you have what we call the rotor. In fact, all the rotating parts are composed of rotor, but this is the rotor. They have the blades. Here you have the hub. The blades are connected to the hub, and modern turbines, they rotate around the longitudinal axis. Okay, there is a blade pitch controller. It makes the blade rotate around its axis. So the hub is connected to a gearbox because it rotates at a very low speed. And you have to rotate the rotor of the generator. So have to multiply this rotation speed here. So you use a gearbox. Inside the gearbox you have epicyclical or planetary gears, and so you multiply the rotation speed. So you have here you have to transmit very high torque because of the low speed. Here you have high speed, so you have small torque. You have some pumping systems here for oil and all this. This is called the bed plate. It must be a very stiff structure because you have to avoid bending of this shaft, and because if this shaft transmits high loads to the gearbox, it will fail in a short time. Okay, this is normally the weak point of the wind turbines. And the nacelle has to rotate in order to face the wind. So you have this yaw platform here. You have a big gear, and it rotates around the vertical axis around the tower. in order to face the wind as the wind direction changes in time. Okay? So this turbine it has a gearbox. This other kind of turbine, we call it direct drive. There is no gearbox. So you have the rotor, and the generator has the static part and the rotating part inside of it. So this is heavier than the previous kind of nacelle, because you have a very, very big generator here. But you don't have to multiply the rotation speed, okay? This is called direct drive wind turbine. And this is a kind of bad plate. Instead of being flat or something flat like the previous one, here you see, this is a bad plate. In that case, this is okay. I wish you good luck, Zhen. no, put the last one, please. The last slide, please. Okay. The last, please. The last one. Yeah, thank you. So, this is an Alstom concept. We call it pure torque concept. Okay, and then Siemens bought Alstom, and then they bought Gamesa, and they're buying everything. So you don't have a gearbox here. So this is heavier, but it's supposed to fail less. But I can tell you that this kind of turbine faces severe vibration problems as well. So as I said before, there are no free lunches in this area. Okay, well, since I stressed the importance of vibration, I just tell you that in the first slide, I won't go back to it, I have three places for students, one for PhD and two for master. I already have support for these students, but I'm interested in this kind of issues. Okay, now I'll put on my glasses and I introduce you Professor Zhen with his long resume. So, please. Now change it to Professor Zhen Gao's presentation, please. So this is his short biography. I'll just read some points of it. So Professor Zhen Gao, he is a professor of marine structures at the Department of Marine Technology at Norwegian University of Science and Technology, NTNU. He graduated in China. He took his bachelor in China and did his PhD thesis in NTNU. He finished it in 2008, I guess, because you told me. I'm not reading it because it's not so easy for me. So his main research areas cover coupled dynamic analysis of offshore renewable energy devices, including offshore wind turbines of all kinds. He is participating in several research projects funded by related to offshore renewable energy. He has published only 152 technical papers. It's just in the beginning of his career. So
That's
he's very young. He published almost nothing up to now.
Yeah.
So he's a member of the specialist committee of offshore renewable energy and a lot of many things. So I introduce you Professor Zhen Gao. Thank you very much, Professor Zhen Gao. Now I give you the word. Thank you for coming.
Thank you.
Yeah, so I will need this. Yeah. Yeah. Well, it works. I'm very glad to be here to give a lecture about offshore wind turbines. Basically, I will focus on design and dynamic analysis of offshore wind turbines. And my background is more related to marine technology. But I understand that there are not so many students here who has the background on marine technology. So I will give some basic introduction about floating structures. And also I want to mention Demetrio because they sponsor my first 5 years of professorship at NTU. So I'm still in this period, that is since 2015. DMGO, if you don't know, it's basically an merge of two ship classification societies. DMV from Norway and GL from Germany. Okay, probably I need to stand here in order to go forward. Yeah. And this is basically the content of my talk. And I will give a brief introduction, focus on offshore development of wind turbines. And then I will mainly talk about design and dynamic analysis, focus very much on integrated dynamic analysis of wind turbines on the wind and wave loads. And then I give some examples of bottom fixed jacket wind turbine and floating wind turbine. Then I'll also talk a little bit about vertical axis wind turbine that has been not really developed for onshore applications. But there might be some advantage of using it for offshore. And then I will just highlight some of the research work we have done or we are doing at the NTNU. So you also notice the slides numbers for different parts, and I will try to break, so take questions for each part. And you will also get this slide after the lecture. So the first part is just to talk about what is a wind turbine and what is an offshore wind turbine based on different type of support structure, bottom fixed and floating. And then also give some of the industrial development of offshore wind turbine, mainly in Europe. Some of the topic has been covered by Professor Demetrio, and I will just quickly go through it. As I understand, I have like 40 minutes for the first part, then we will have a half an hour break, and then I continue for another more or less 2 hours. Yes, before I start, I just also briefly mention other type of marine renewable energies that we have been developing or using. And the wind turbine, of course, you understand that we try to bring the kinetic energy and basically to generate electricity. And we have also other type of resources in the ocean space, like tidal due to the current, tidal current, and ocean current. Or we can also use wave energy converter to convert the kinetic energy in the wave propagation with different devices. And then there's also other types of conversions. But I want to highlight that except the wind turbine, which has been more or less commercialized, or offshore is on the way for fully commercialized, the other type of, in a way, marine renewable technology has not been so mature to be commercialized. And basically they are quite costly to develop the technology to convert different energies into electricity. I will briefly mention this later on. So today we will mainly focus on offshore wind turbines. And this, of course, due to the development onshore wind turbine, we have very good basis for offshore development. And basically we change the support structures for offshore application. You have put it into the water. And here also shows some different types of wind turbines with different support structure. Basically you see the same type of turbines, but support structure might vary. Basically we have monopile jacket, spar, which is floating one, and semi-submersible we could also have TOP type of floating wind turbine. I will discuss this later on. It's not working even here. Okay, I just briefly mentioned the wind energy that is available in the wind, and this is kinetic energy, and through a cross-section area, normal to the wind direction, and with a given wind speed. So basically, it's a cubic term of the wind speed. And that is also important fact that if we have large mean wind speeds, and then we will get more available wind power. If you multiply with time, you get the energy. And here also illustrates some of the potential of onshore and offshore applications. There's a theoretical potential, but it's not really possible to use all of these wind powers. And there's evaluation of technical potential, for example, for offshore, range from 15 extra joule per year to 130. And just remember that the total electricity generation in the world in 2015 is about 87 joule. So basically, it's possible to cover all of the energy generation from offshore wind. But theoretically, it's not, we will do this. We rely on other type of sources to generate electricity. So this is better. Yeah. Good. And another point I want to show is that usually we have relative stable and large wind speed in the offshore area. So here it's just showing a map of wind speed map in the area of Europe, and this is Norway, this is UK, Ireland, and the mainland of Europe, and this is North Sea, Norwegian Sea, and this is Mediterranean Sea. And you cannot really read the figures here, but relatively speaking, if we move to north, we have relatively larger mean wind speed. Here I give you some examples. At the 100-meter height, we have annual mean wind speed about 9.5 meters per second at the North Sea area, where we found most of the wind turbine in Europe, offshore wind turbine in Europe. Yeah, then I can move. If this works, I can just stay here. It's better. Yes. So basically, for modern wind turbines we see today, they are quite standardized turbines. So you basically see 3 blades with horizontal axis, and also you have upper wind. So wind blow to the turbine blade first, and then the tower. And also for modern large-scale wind turbine, you have this possibility to change the rotation speed for low wind speed, so that you have the maximum power absorption. And then you have also possibility to pitch the blade to regulate the power for high wind speed. That we'll talk about later. So basically, a turbine is convert kinetic energy in wind and into the rotation, mechanical energy in the rotor, and then you have a generator connected, which basically transform into electrical energy. So this conversion is important, and later I will show you some of the efficiencies of these 2 conversions. And as Professor Demetrio mentioned, that actually the heart of wind turbine is this part, the nacelle, which contains a typical gearbox, which converts the low rotation speed. For example, for a 5 megawatt turbine, rotor operates like 12 RPM, and then you have to connect to a generator which rotates very fast, 1,150 RPM. So you need to have a gearbox to convert this rotation. And if we look at different status of operation of wind turbine, and this is actually showing the thrust coefficient as a function of so-called actual induction factor, which basically defined as a reduction of the wind speed at the rotor plane as compared to the inflow velocity. So if we look at this stage and the wind turbine, wind blowing in this direction through a wind turbine, then you would have a force which is along the wind direction acting on the turbine. And oppositely, you would have force acting on the wind, which slow down the wind speed. And so basically, you have an expansion of the wake, and the wind speed will be slowed down at the far wake. And then, of course, you also attract the wind power. And if you know also propeller for a boat, and they actually operate in opposite direction. So the vessel moves in this direction, and the flow direction is this. And the thrust force actually acting oppositely to the flow direction, and which actually, from the fluid point of view, accelerates the water. So you would have a contracted wake, and which has a larger velocity. So this is the thrust force is moving the vessel forward. So they operate in different regions. And of course, if you also look at the wind turbine case for larger actual induction factor, and then they will have a wake effect. And most of the turbine actually operate in this region, where also later we'll talk about the blade electric moment theory. So this is important to understand the physics between the force acting on the rotor and force on the fluid domain. And this has already been shown, and theoretically we have a limit that how much the wind power can be attracted or absorbed. So there's about 60% highest. And in principle, if you try to absorb all of the wind power, then the wind has to be stopped at a certain point, because the velocity has to be zero. And that is not practically possible. So wind has to go through the wind turbine, and with reduced wind speed, and then you attract wind power. And the modern wind turbine has a very good efficiency as compared to this number. It's about 50%. And these are mainly referring to the aerodynamic efficiency. So that is related to the conversion of the wind kinetic energy to the rotor mechanical energy. But then you have also this gearbox and the generator. We have another efficiency, train efficiency, which is very high in theory. So you don't have much loss due to this conversion. And the wind turbine control is also important because naturally we have varying wind speed from day to day, from time to time. So you do not have really very good constant wind speed that you can design an ideal wind turbine for. So here I just plot the different power as function of the mean wind speed. And it's not very clear, but we are showing in cut-in wind speed and rated wind speed, cut-out wind speed here. And these are the available power in wind. And this black curve showing the typical power curve for a modern wind turbine. And this for small wind speed, below rated values. And you operate the turbine so that when the wind speed increase, you increase the rotation speed. So you achieve the maximum power coefficient, CP. While reach to the rated wind speed, you want to regulate power to have a constant power output, which will be good for the grid connection. And then, of course, later we will also see that the loads will be reduced. So these are, and also this is the rotation speed curve. So basically it looks like this. So it's important that wind turbine designed for different operation wind speeds. Here also I show some of the wind turbine characteristics and in terms of power dimension. And here also show the years that the maximum power of wind turbine enter into the market. So you can see that, say 20, 30 years ago, it's only a few hundred kilowatts, but now it's about 8 megawatt turbine that is already entered into market. So basically, you can say that in older days, we can use one turbine of today to replace a whole wind farm. And wind turbine blades, they are not very heavy. They are made of composite material. And this is basically to reduce the gravity loads when it's rotates. But they are pretty long. And for example, a 5 megawatt wind turbine, it's 60 meters of length, so diameter of 120 meters. For 8 megawatt turbine, it's about 82 meters. So there's a Airbus airplane 380 with a wing length of 40 meters. The wind span is about 80 meters. It's the same as the single wind blade for 8 megawatt turbine. And the weight is, I mentioned, on a few like 15 and 35 tons. And they have to put on very height, to the harbor height, and basically in order to have a certain gap between the wind turbine tip to the free surface. And I just forgot to mention that when we look at the wind turbine, we all call it like 5 megawatt wind turbine. That will refer to the rated power of the turbine. So that is the maximum power you can get from a turbine. And as I mentioned, the wind turbine have to work on 4 different wind speed. And then there's a so-called capacity factor, which is the ratio between the average power to the rated power. So because on land you typically get 25-35%. So that means about 30% of time that the turbine is working on the rated power. Offshore we have more steady state conditioning of the wind. You have relatively larger capacity factor. And just to give an example, a 5 megawatt wind turbine with a capacity factor of 40% can supply roughly 1,500 households in that order. And I mentioned the material for blades, and if we look at gearbox, nacelle, tower, support structure, they are basically steel structures. And there are also concrete structures that are used for support structures. Most of the wind turbine today use gearbox, as I mentioned, convert to low rotation speed of a rotor into high rotation speed of generator. And there's also development of direct drive or hydraulic systems for conversion. Okay. Yes, now I will start to talk about offshore wind turbines and start with bottom fixed turbines. So the offshore development is really rely on onshore, and then we move slowly to offshore into shallow water and then to deeper water. This is a very natural development. It's also a cost-related issues. But here I already show some of the foundations for support structures, but most of them actually rooted from oil and gas, offshore oil and gas industry. But in older days, offshore oil and gas development, they even use like a jacket foundation for about 400 meters water depth. But now these days, of course, we will probably use floating support structures. And water depth is really playing a very important role to find the most optimal support structure for developing offshore wind turbines. But of course, oil and gas platform, they are usually one of its kind. So you don't have many actually produced at one time. But for wind turbine, you develop in the wind farm usually consists of 50 to 100 units. So there's a a bigger advantage to use mass production or mass installation to reduce the cost of energy. And not only fabrication, but also installation is very important. This is a particular issue for bottom-fixed wind turbines. And for example, for monopower wind turbine, this is just a single hollow steel cylinder which has to be hammered into a seabed. Upon that, you install transition piece, tower, and blades. So all of this operation has to be done offshore and with support of installation vessel. In this case, is a floating installation vessel, and in this case, is a jack-up installation vessel. So to use standardized wind turbine component and to accelerate the installation procedure is very important. For example, these operations can only be carried out in relative small sea states. So for example, in North Sea area, you can do this installation only during summer season now. So you cannot really do this in winter. So this is a big issue related to the cost of the wind turbine development. And if we move further offshore, when the water depths getting larger, so ideally we will use so-called floating structures. And basically they are like a float, like a ship or platform with mooring lines, just to keep them in position. So different concept has been introduced. SPA, it's just a cylindrical structure with a heavy ballast at the bottom to achieve the hydrostatic stability. And semi-submersible, you have multiple columns to get restoring due to the waterborne area. Or you may have so-called a tension leg platform, where you have larger buoyancy than the gravity of the system, so you have pre-tension in the mooring lines when you have the installation to achieve the hydrostatic stability due to the tension in the tendons. So here just showing some of the three basic disciplines to achieve hydrostatic stability and the corresponding mooring lines. And here I also show some of the examples. This is so-called high wind concept, which is developed in Norway by Statoil. And this is a concept called the wind float, which is developed in the US by Principal Power. They have already, Statoil has tested at the sea since 2009, a 2.3 megawatt high wind turbine. And they just installed a small farm of 5-6 megawatt units in Scotland with the same SPA technology. And the wind float, they installed, tested the first prototype with a 2 megawatt Vestas turbine in Portugal, and that is in 2011. And last year, they decommissioned this project. So they bring back the floater to the shipyard and dismounted all of the components. So fully finished the small lifetime cycle. The other concepts are just, or types of floating structure are just the concepts, and they have not been entered into any prototyping and testing phase. And yes, and we will have more flexibility actually for floating wind turbines to choose different configurations and to explore different possibilities as compared to on-land wind turbines. So there's a variety to use horizontal axis wind turbine or vertical axis wind turbine. Later I will discuss more on this. Or we may use, say, 3 or 2 blades and or upwind, downwind turbines. And I also want to mention some of these, actually there are 3 turbines that is under testing in Japan, 2 megawatt turbines and 1 7 megawatt wind turbines. So Japan is also developing floating wind turbine significantly in recent years. And also I mentioned some of the area like in US, Mediterranean Sea, Japan, or northern part of North Sea, Korea. There's a good site for floating wind turbine. It's basically because the water depth is large. So it's not really economical viable to use bottom fixed turbines because you have to have a very large support structure, it will be very expensive. Here is some of the industrial development of different types of foundations and bottom fixed and floating ones. And as I mentioned, water depth plays a very important role to find the most suitable foundation for different water depths. So it's not really very clear at which water depths that floating wind turbine will become more competitive as compared to the bottom fixed one. At the moment, of course, you have extra materials in the floaters and extra material in the mooring system of cables, which makes the floating wind turbine relatively expensive. But probably in the order of 100 meters, that floating wind turbine will become more cost competitive. There's also very important software development since 2005, which is actually initiated by International Energy Agency. NREL in the US has been playing a big role in this benchmark study. And they started with code-to-code comparison, and actually now it's ended into the code-to-model test and code-to-field measurement comparison. So it's very important that this is ongoing and bring a more reliable software for design and analysis of wind turbines. Meanwhile, there's also international standards that is on the development. They rooted from the bottom fixed design laws for bottom fixed offshore, for on-land wind turbines, and then move to bottom fixed offshore and then floating wind turbines. And what time is it now? Well, that's good. Here I show some of the trends in offshore wind development. And the important trend is that in recent there's a big cost reduction in offshore wind turbine development. It's basically due to the fact that we are using larger scale turbines and designing more optimal support structures and also reducing the installation, operation and maintenance cost. Up until now, it's about 15, 16 gigawatts offshore installed in Europe. So it's not a big amount as compared to the total on land or total installed wind capacity, which is about 500 gigawatts by now. So, but it will increase, and basically it's about annual increase is about 30%. So every 3 years you have double the installed capacity. And here is showing, it's not very clear, but it's showing different size of turbines that is in the market or in the farm that is installed in different years. Here is showing the megawatt turbine, which is smaller than 3 megawatts. It's a majority. That is from 2001 to 2005. And then we have increased turbine 3 to 5 megawatts for the next 5 years, and then the next 5 years increasing more. And in the future, there are more orders like using 5 to 8 megawatts, even about 8 megawatt turbine. So there's an increasing use of large size turbines. And basically you will reduce the cost of installation and maintenance per megawatt if you use large turbine. And also, I think a floating wind turbine will also be developed and will play a relatively important role. And there are not so many at the moment. Totally maybe about 40 megawatts in total. And here it's not very clear, but showing some of the places that is developing floating wind turbines. And naturally, the developers, they first test prototypes or a single unit, and then develop into a small farm, a few units, like 5 units, and then go further with large commercial size farm, typically 50 to 100 units. So this is a very natural development. And I believe that in Brazil you have relatively large water depths, 1,000 meters. So it might be very difficult to use cost competitive wind turbines. But of course, eventually, if you use, probably you will use floating wind turbines. And here I'm showing some of the levelized cost of energy or cost of electricity, and just try to compare different renewable energy electricity generation. I don't show all of the details here. This is from 2015, and the units here is euro cent per kilowatt hour. I'm showing the basic average of the onshore wind turbine and offshore wind turbine, and compared to the relatively small size hydropower. And here it's showing like about, well, I even cannot really read, about 60 euro cents per kilowatt hour for onshore, which is comparable to small hydropower. And offshore is more or less twice as expensive as onshore at the moment. And here is some prediction towards 2030. And also they're showing some of the cost estimates during the bidding process for some of the offshore wind farm in Europe. Here is different units, euro per megawatt hour. So we are expecting that this blue showing the overall decreasing of the levelized cost energy towards like 60 euro per megawatt towards 2030. And this will be then same as the on-land wind turbine price we have today. So this is very important, and this is also mainly due to the use of large-size wind turbines. And it's a very good trend that it's decreasing and towards a more commercialized turbine. And I also want to mention that in some of these farms, actually, during the last 2 years, during bidding process, and they asked for 0 subsidies from the government. So that means in the future they will really commercially operate their wind farms. And in the beginning of development of offshore wind turbine, you actually see an increase in the cost of energy, but due to the mass production and better installation, maintenance, and so on, then it's reduced. Here I also show some of the cost components, and for onshore wind turbine and for offshore bottom-fixed wind turbine. We don't have commercial floating wind turbine yet. And you can see that support structure will play an important role. Basically, you have needed to have a larger support structure for offshore development. And also operation costs will be relatively high as compared to on land, because it's not easy to reach offshore wind farm, especially in bad weathers. And and typically it will be 20–30% of CapEx, capital expenditure for the lifetime cost. And by the way, offshore wind turbines, they are usually designed for 25 years of lifetime. And of course, in the future, most of the offshore wind turbines have not reached the lifetime yet, because they developed recently. But the first wind turbine offshore wind farm, which is in Denmark, and they just decommissioned the last year. It's from 1991. But the individual unit is about a few 100 kilowatts. So they are relatively small as compared to today's wind turbines. And later on, there will be naturally a problem whether we can extend the lifetime of wind turbines by its actual use of the structure and so on. So basically, we rely on increasing wind turbine size, improve manufacturing infrastructure that is also related to grid to reduce the cost of energy. Yes, I just stop here, and I will be glad to take any questions. And probably we will also have a break now after the questions. Any questions? Yes.
Good morning, Professor. My name is Ulisses from Brazil. The last slide, you show us that the cost of offshore turbine is less than the offshore is less than onshore. But when we construct the equipment, we already prepared to inch protector, and I imagine that the cost of offshore, because the sea is higher than the
Yeah.
the onshore. Why?
Probably
I
I'm
don't
not
understand.
very clear about here. This is a percentage of the cost to its own. Like if it's onshore wind turbine, what is the percentage of cost for different parts? And if it's offshore wind turbine, what is the percentage of different parts? And as I mentioned, that the actual absolute cost of energy for offshore is about twice of onshore. So the absolute value for the offshore is much costly, but the components is also, there's also big part of substructure that is costly for offshore. It's natural that you have to put a larger substructure in the water. Yeah.
Okay, thanks.
Professor, thanks for your presentation. So good. I would like to compare. Can you explain roughly if we have 5 megawatts, for instance, if you compare a vertical axis and horizontal axis, which is better?
Well, I will particularly mention vertical axis wind turbine in my later presentation, so you will get an idea about this comparison. We also have done some comparison for floating vertical axis wind turbine and horizontal axis wind turbine, and then you also see the results. Yeah.
Okay, thank you.
Yes. I will have many breaks. Later you can ask.
No. I also have curiosity. See, Professor, the last slide of, not your last slide, but the former presentation from, they talk about direct drive wind turbine, which should be more reliable, and at least it was, I understand, and I do not know if you will approach it, this kind of comparison, direct drive wind turbine with a gearbox, if there is any kind of efficiency gain, because when you have a direct drive, you know that you could generate electricity in whatever, of course, inside the range, but whatever rotor speed, because you can treat the energy as you like, and with gearbox you don't. You have to, if you are connected to the grid, you have to stay in their frequency. So which will be the gains and the losses of this kind of technology? Because I'm studying not wind turbines, but I'm studying turbines with direct drive generators or gearbox generators?
Yes, I'm not an expert on this drivetrain and issues, but most of the turbine used today rely on gearbox. And the problem with that is that you have mechanical components of gears, and then you may have damage there. And also there will be lubrication issues. So there's always maintenance issues. And you have to also design the gearbox so that you have the load capacity for 25 years and so on. So I'm not very sure about the direct drive, but you will have less mechanical components. It's mainly electrical and electrical. And then it's, but what I understand is that usually for the same megawatt, and you have large weight of direct drive, and which is not really beneficial for a floating wind turbine, because then you would, when it's smooth, will induce larger loads in the tower and so on. So that is also one concern. But I don't know the future development. There's a lot of companies now pursuing the direct drive. Yeah. Maybe you can comment.
Thank you, Gal, for this first part.